Okay, so we've got a tennis ball initially moving with a velocity of 28 meters per second to the right, and a tennis racket strikes the ball. So a tennis racket, we've got some velocity VR, and then we're going to strike the ball. I'm actually just going to draw it like this. And the ball is going to leave at 28 meters per second. And then presumably our racket will be forced backwards. And so if we treat the collision as perfectly elastic, and we treat the ball as a particle of mass 0.0580 kilograms, and the racket as one of 0.261 kilograms. So the first question is, does the speed of the racket change as a result of the collision? So first of all, so if it's an elastic collision, then our delta KE is 0. So our initial kinetic energy is 1/2 the mass of the ball times the velocity of the ball squared, plus 1/2 the mass of the racket, the velocity of the racket squared, or the speed of the racket squared, I should say. So, and then our KE final. I'm going to put little eyes on this to say that these are the initials. The speed of the ball final squared plus 1/2 mass of the racket, velocity of the racket final squared. Okay, so if our delta KE is 0, that means that our KEI equals our KEF. So 1/2 mass of the ball, velocity of the ball initially squared, plus 1/2 the mass of the racket, velocity of the racket initially squared, Now, we're given that the speed of the ball, it's changed directions, but it's 28 meters per second in both cases. We don't need to worry about the mass because we can see here that as the mass isn't changing, that these guys are actually going to cancel, leaving us with 1/2 mr VR initially squared is equal to 1/2 mr VR finally squared. And obviously these 2's will cancel and these masses will cancel, and we can take the square root and find that our velocity of our racket initially is equal to the speed, I shouldn't say velocity, the speed of our racket finally. So our speeds are constant. So for A, the speed does not change. Alright, so for B, it asks what the total momentum of the system is. So P total, we can either do it initially or finally, so we could use mass of our ball, velocity of our ball initially, plus mass of our racket, velocity of our racket initially. And this is actually a vector quantity, so let's Throw those in there. And so I'm not sure how to do this without actually knowing our racket's velocity. So use our final momentum, which is mass of a ball, velocity of the ball finally, plus mass of our racket, velocity of our racket finally. And so we know that PI equals PF. I'm just going to change that from total to I. Or mass of our ball, velocity of our ball initially, plus the mass of our racket, velocity of our racket initially, is equal to mass ball, v ball finally, plus mass of our racket, velocity of our racket finally. So we can rearrange this equation to just bring each of our components on either side. So VBI minus VBF, mass of racket, VRI minus, or VRF minus VRI. And we can see here, and we know that our VRF is equal to our VRI, so our magnitudes are equal. But on the left here, we can see that we have mass of ball times minus or plus 20 meters per second. Oh, sorry, 22 meters or 28 meters per second. And then the final speed is a minus 28 meters per second. So then on the left it's non-zero. So then I'll just leave this in like this. So on the left it's going to be non-zero. In fact, it's going to be MB times 56. And so our velocity finally for our racket must be the negative of our initial. And so then this would be minus VR initial, or our racket, our racket's initial velocity must be minus MB over MR times 56.0 meters per second divided by 2 as well, because there's going to be 2 of them. Okay, and so then our racket's initial velocity is minus the mass of the ball, 0.0580 kilograms over 2 times the mass of the racket, 0.261 kilograms, times our 56.0 meters per second, which comes out to be 6.22 meters per second. So our initial velocity of our racket is minus 6.22 meters per second. And so that then the total momentum is just one of the two, either initial or final. So we can use the initial. So it'll be mass of ball, V ball initial, plus mass of racket, V racket initial. I'll put these where I had them before. And so that's 0.0580 kilograms times our velocity initial for a ball, 28.0 meters per second, minus 0.261 kilograms times our 6.22 meters per second. So I guess plus, and I'll put the minus in here where it belongs. If we work this out on our calculator, it comes to 5.8 times 10 to the minus 4 kilograms meters per second. So that's the total momentum for our system. Again, I don't know how I would solve for the total momentum without knowing that velocity. Except in a roundabout way, but it's easier to solve for the velocity before the momentum, I would think. But oh well. So here we go. So if we check to the solution here, the speed of the racket doesn't change as a result of the collision, so that's good. Determining the total momentum. So we can either use, so here they've used the finals, and the final speed of the tennis ball is 28. They've set it to 0, but that doesn't make any sense, because if the speed isn't changing, then why would it be 0? That sounds like the speed is changing. And so the total momentum is 1.6, so that's a little high, since I've got 5.8. And then using their total momentum, so they're saying, so right here, it's saying that the initial velocity of both is just the final velocity of the ball, but if the speed of the racket isn't changing through the collision, then they're representing the speed is changing. So yeah, so part B and C are done incorrectly. Speed of racket doesn't change through collision. So if the racket speed doesn't change through the collision, then it can't go to 0. That doesn't make sense.